Hi, in this section we get to talk about limits of continuity. So we really get a step away from the intuitive approach to limits to introduce the derivative eventually. And we get to learn more about graphs that will have breaks or jumps in them. And we will learn the mathematical terminology associated with this concept and do applications. Okay, so let's start out with the definition. Let f be a function and let a be a number in the domain of f. Then f is what we say continuous at a if the limit of f of x as x approaches a exists and the limit of f of x as x approaches a equals f of a. So just an aside, remember that the limit of f of x exists as x approaches a if we have that the limit of f of x as x approaches 1 from the left, or we're not looking at 1, so let's just say a from the left is equal to the limit of f of x as x approaches a from the right. So that's what we mean whenever we say the limit of f of x exists as x approaches a. And additionally, we have the limit of f of x as x approaches a is equal to f of a. So in other words, you can actually substitute a into your function, and that's your limit. Okay? So that's what it means for us to have a continuous function at a. The function f is said to be continuous on its domain if it is continuous at each point in its domain. Okay? Move this up a little bit. If f is not continuous at a particular a in its domain, we say f is discontinuous at a. Discontinuous at a. Or we say that f has a discontinuity at a. A couple of notes. A discontinuity can occur at x equals a if either the limit of f of x as x approaches a does not exist, or the limit of f of x as x approaches a exists but is not equal to f of a. Okay, so we can say that we have a discontinuity in either of those cases. Another definition, move this down a little bit. If f of a is not defined but f of x is defined for at least some values of a of x arbitrarily close to and on both sides of a, we will say that f has a singularity. It has a singularity at a, or that a is a singular point of f. Okay, so if f of a is not defined, but f of x is defined for at least some values of x arbitrarily close to and on both sides of a, we will say that f has a singularity at a, or that a is a singular point of f. Okay, so note the difference between a singularity at a and a discontinuity at a. Okay, so let's look at some examples to make sure we understand this idea of singularity and discontinuous or continuous. Okay, so we are going to look at exercises from the book because you have the graph drawn and you don't have to worry about what I'm sketching. So we're going to do numbers 2, number 6, number 8, and number 10. Those are the ones we're going to look at here. So we have to, in these exercises, look at the graph of the function f. Determine whether f is continuous on its domain. If it is not continuous on its domain, we need to say why. Okay, So we look at this function. Notice that this graph doesn't have any breaks. Notice that it we can say that this function is defined for every element in its domain. Okay? So the function f is said to be continuous, right? Because it's continuous at each point in its domain. So we have that this one is continuous. Okay? Number six. Notice that we're good to go as we're going along, but then we get to this part of our function and notice that there's an open circle, but it's closed up here. Because this is an open circle, and this occurs when x is equal to 1 here, we say that the function is discontinuous at 1. So notice that this function is discontinuous at x equals 1. And furthermore, we can say that because if we look at the limit, let's go back to the definition of continuity on the previous page. If we look at the limit of f of x as x approaches 1, we should get the same thing as f of 1, right? But notice the limit as x approaches 1, as x is approaching 1, our function is approaching negative 1, right? So we'll say that that's equal to negative 1. However, f of 1 is this closed circle, which is 1. So notice that that's not equal to f of 1. If our function were continuous, that would be the same. Okay? So we have our discontinuity at x equals 1. Okay? Now let's examine the graph in number 8. So we have this graph, we're going along the function, closed circle here, but then we get down here, you have an open circle, and then the function goes up. It increases to infinity. So notice that here, because you have this closed circle here and this open circle here, we have that the function is discontinuous. So discontinuous at x equals 0. So notice we're not saying what the y value is, we're saying where the discontinuity occurs with our x. Okay? Now, notice that the limit, and this is just further justification, the limit of f of x as x approaches 0 does not exist. Does not, we can make that n a little bit better. It does not exist. Okay? Since the limit of f of x as x approaches 0 from the left does not equal the limit of f of x as x approaches 0 from the right. So as x approaches 0 from the left, our function goes here. But as x approaches 0 from the right, our function goes here. Two different spots, two different values. Okay? So it does not exist. Now in number 10, we have this example, this graph. Notice that nothing's wrong with it. We have no breaks, and it's continuous everywhere on its domain. Everywhere the function is at, or everywhere the function goes, it's defined. So we say it's continuous on its domain. Okay, so now we've gone through enough examples here where you can go through the remaining ones for your homework. Okay, let's make sure we talk about singular and discontinuous and continuous. Make sure we understand all of the ideas. So in exercises 17 through 24, the graph of a function f is given. Determine whether at the given point A, f is continuous, discontinuous, or singular. So we're going to look at the following values or following examples: 18, 20, 22, and 24. Okay, so we have number 18, we have this function. Notice that the arrow keeps going here, so that indicates it's going to negative infinity. Here the arrow keeps going up, so it's approaching infinity here. So we want to figure out what happens when a is at a equals 0. Notice that at a equals 0, this is an isolated point where our function is not defined. Because our function is not defined and that's an isolated point, we say that our function that's given is singular at a equals 0. So for 18, we have it is singular at a equals 0 because it is an isolated point at which f is not defined. Okay, now 20. Looking at 20, we have our graph, function goes up, and we're concerned about what's happening at the given point a equals 0. Notice that when a is equal to 0, our function is actually continuous. It's defined there. So we say our function is continuous at a equals 0. Because remember, we say it's continuous if we have the limit exists. It does exist. And as x approaches 0, that's equal to f of 0. So we're good to go. Okay, we have a continuous function at a equals 0. Or we're concerned about what happens at the point a equals 0. So the function is continuous at a equals 0. Okay, so 22. 22 is a little bit more interesting. We look at this graph, we get here, there's an open circle, then it goes here and has an open circle, and then it goes down here, it's closed circle, and then it goes up. Okay, so we examine this function. We want to find out what's happening at a equals 2, which is right here. We have a lot happening. Notice that the left-hand limit as x approaches 2 from the left-hand side, that's 0. As x approaches 2 from the right side, our function is approaching -1. Well, though 0 and -1 are not the same, right? So we say our function is discontinuous since the left and right limits at 2 do not agree. Okay, and then 24, notice that here we have a function that's going, then it has an open circle there at 0, and then we have this function here and it's an open circle. So essentially it's 22 except for we've removed the closed circle. Okay, we're still concerned with what happens when a is equal to 2. But now, since we've taken that closed circle away in this graph, it turns out that now, since we're concerned about an isolated point where our function is not defined, then that makes this function singular at a equals 2, right? Since it being your function, or since it being a is an isolated point at which f is not defined. And make sure you understand the difference between 22 and 24, right? Because 22, even though we had open circles here, the function was actually defined because there's a closed circle. But here, function is not defined because we have nothing but open circles. So notice the difference between discontinuous and singular. Okay? Perfect. So now we are going to do two more examples, and they are going to be number 26 and number 28. So for number 26, or in these exercises here, it says use a graph of f or some other method to determine what, if any, value to assign to f of a to make f continuous at x equals a. So it says that essentially we have something going on at a equals -1. How do we make this function continuous there? So notice it's not currently, because if we substitute -1 in, that gives us 0 in our denominator. We can't divide by 0. So let's sketch the graph of 26. So if we sketch the graph, you'll have something like this. So this would be -2. This would be 2. And you'd have that open circle at -1. So that's what the function looks like. Now it says we have to figure out what we would assign to f of a to make f continuous at x equals a. So at a equals -1 here, the limit of f of x that value is 1. The limit of f of x as x approaches -1, in order for it to be continuous, we will need that to be equal to 1. Okay? So f of -1 would be equal to 1, makes f of x continuous at -1. So what we've observed here, the question is saying use a graph of f or some other method to determine what, if any, value to assign to f of a to make f continuous at a. So for it to be continuous, this needs to be defined, and notice that the limit has to exist. So as x approaches -1 from the left, our function would approach 1. As x approaches -1 from the right, our function approaches 1. So in order for this function to be continuous, we know that the limit of f of x as x approaches -1 has to be equal to f of -1 in order for it to be continuous. We know this is 1, so f of -1 equals 1 would have to make our function continuous at -1. Okay? So now let's look at number 28. Number 28, here we have x squared minus 3x divided by x plus 4 is our function, and we're concerned about how we could make our function continuous at a equals -4. Well, this function is a little bit different. So for this particular function, there's a vertical asymptote. So there is a vertical asymptote at x equals -4. And you can graph that on your calculators. It's good practice. Because there's a vertical asymptote at x equals -4, that means that the limit of f of x as x approaches -4 does not exist. So because it does not exist, that means there is no value. So no value of f of -4 will make f of x continuous at -4. Okay? All right. Well, that concludes our section. That talks about our limits and continuity. For more examples, go through the homework. Another example that's really, really neat and worth trying out is number 38. This is a fun one too. Okay. Number 38 is actually fun because it says use a graph to determine whether the given function is continuous on its domain. If it is not continuous on its domain, list the points of discontinuity. Let's just go ahead and do it. I said we were done, but why not just go ahead and do it since I've already talked about it and it's here. F of x is equal to this piecewise defined function. It's 1 minus x if x is less than or equal to 1. It's x minus 1 if x is greater than 1. Graphically, you have the following. We have the function is 1 minus x. I'll use green for 1 minus x. 1 minus x is the graph going through 1, and then you have here, that's the graph of 1 minus x. It's the graph of negative x shifted up 1. Remember, negative x is decreasing, so at this point, that's 1 at this point. Okay, so that's our graph. But then I'll use blue for x minus 1. X minus 1 says we take the graph of x and shift it down 1. And what that does is that means we have this as our graph for x minus 1. Okay? Well, what happens? If we put it all together, it turns out that that function is actually continuous, or that piecewise defined function is continuous on its domain, right? Because if we follow it along, there we know that the limit exists everywhere, and we have that the limit of f of x as x approaches any value a is actually equal to f of a. So it's continuous on its domain. All right, have fun working through the homework and doing more with limits.